Okay, so homework was what we did in class last time was we converted from a decimal number to the equivalent binary number, right? So homework was to write code that has a binary number represented as a string and converts it into the equivalent decimal number, right? Okay, so let's look at this guy. So for example, if we were to take in this string right here, that string right there, it should give us the number 221. That's the desired result of our code, right? Okay, so we want to think about how this should actually work. And what I'm going to do, well, we can make it work for that. So I'm going to steal some stuff here. Always, 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 always start off by drawing pictures and solve the problem on paper first before you dive into the code. Okay, so we're going to look at this. So this is a 1, this is a 1, and these are actually, I'm going to represent them how they actually are. This is the char 1. This is the char 1. This is the char 0. This is the char 1. So we got 3 1s, then we need a 0. And we need one more 1. All right, so 1 1 0 1 1 1 0 1. Okay, and then we're going to, we need 3 more of those guys. And this is bucket 5, bucket 6, bucket 7. Okay, so that is what our string actually looks like. That make sense? All right, now what we want to do is we want to think about, well, how do I convert this value like this into its decimal equivalent? Well, we got to think about which pattern we are looking at. So what I'm going to do is I'm going to write another line beneath this. And this is the 1's place. This is the 2's place. This is the 4's place. This is the 8's place. This is the 16's place. This is the 32's place. This is the 64's place. This is the 128's place. Right? And we'll color code this. So we'll make that in red. Now, just to remind us what this stuff actually represents, we're going to be very verbose here. This is the 2 to the 0th place. This is the 2 to the 1st place. 2 to the 2nd place. 2 to the 3rd place. 2 to the 4th. 2 to the 5th. 2 to the 6th. 2 to the 7th. All right, that makes sense? So this starts off at 1 because 2 to the 0th place is 1. If this was a base 8 number, this would also start off at 1 because 8 to the 0th place is 1. Anything to the 0th power is a 1. All right, so we start off with a 1. We multiplied it by 2 to get a 2. We multiplied it by 2 to get a 4. You multiplied it by 2 to get an 8. We multiply it by 2. We multiply it by 2. We multiply it by 2. Starting to see a pattern there? Okay? And when we do something through repetition, what's our Home Depot tool for doing something like that? For a loop, or a loop, some kind of loop, right? Then we decide which kind of loop we might want to use. All right, similarly, when we're solving this problem by hand, I would start here at the end, right? Now, as a human being, I would say, I would solve it this way. I would say 1 times 1 plus 0 times 2 plus 1 times 4, so on and so forth, dot, 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 plus 1 times 128. Right? That's what that pattern is? All right. Now, we have a limitation, though, right now. This is not the number 1. This is the character 1. Now, do we have a tool that allows us to convert that guy, convert a string or a char type to an int? We do. It's called int. We have a function called int that I can toss a char or a string into, and it will spit out the numeric version of that. Okay? Now, there's a float function for doing it on the float side. Okay, but we know about the int one. But we're going to do this we're going to solve this a couple different ways. First of all, we're going to solve it the binary way. Now, what I mean by that is, did I waste my time doing this math right here? 0 times 2 is a waste of time, right? Because it's always going to be 0, and anything plus 0 will be that anything. Okay? So really what I'm going to do is, as I'm going through here, I'll start at the end of the string, and I'm going to say, this guy, if it's a 1, add a 1. If this guy's a 1, add a 2. If this guy's a 1, add a 4. If this guy's a 1, add an 8. So we're asking a question. We're going to go from the end of the string to the beginning of the string, okay, walking one step at a time. So we want to solve that problem. So we're going to loop from end of string to beginning of string. Right? Each time through, we're going to say, if we are looking at a 1, add the current place to a running total. Finally print the running total. So maybe we could say, when finished walking through string, print the running total that we've built up along the way. All right, so we're going to solve this in little pieces. So first, we're going to have our input. So this is going to be our string. We can ask the user for this if we want, or we can hard code it. But we want our logic to work generically, where it doesn't matter what that string contains, as long as it's zeros and ones, it'll do this math for us. All right, so we're just going to write some code that walks that string from the end to the beginning and prove that we did that. I'll just print out a character each time, just proving that we walked it backwards. Okay, so taking little tiny steps. All right. All right, so here is my binary number. I want to write a loop that goes from the last legal bucket of this guy to the first legal bucket of this guy. What position is the first legal bucket of this guy? Bucket 0. What position is the last legal bucket of this guy? What if I told you that this string here had a bunch of stuff in it, and I asked you, so the question mark is legitimately like, we don't know. What if I asked you, what is the last legal bucket of the string contained in binary? How could you generically tell me that?
It's the length of binary minus 1.
Length of binary minus 1. All right. So this is bucket length of binary minus 1. Why isn't this? My keyboard's not working. Oh, there we go. This is bucket length of binary minus 1. This is bucket 0. All right, so we want to loop, so we're going to say for I in range. Now, if we don't want to say I, in fact, I'm going to spell this out a little bit more. That way you don't think we always use I. So I might say cur pos in string. Be really verbose, right? For cur pos in string in range of, we're going to go from the length of binary minus 1, that's the last legal position, all the way up to, but we want to include bucket 0. So we're going to say to -1, step by -1. All right, so I'm going to, if I started at bucket 7, this is going to go 7 minus 1 to 6, minus 1 to 5, minus 1 to 4, blah, 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 minus 1 to 0, minus 1 to -1. And that's where we finally stop. That makes sense? That's what kicks us out. So by saying -1 here, we're saying I want to go all the way up to, but not including, all the way down to, but not including that value. Make sense? So that's why I say the -1 there. This -1 says, how am I going to change the value of cur pos in string each time? All right, so for right now, what we're going to do is we're just going to print out binary at position cur pos in string on its own line. So it should print out a 1, then a 0, then a 1, then a 1, then a 1, then a 0, then a 1, then a 1. That kind of had a good, it was kind of dancing music, I think. All right, so we're just going to get confident that this tool that we've put into play here is doing what we want it to do. Okay, we're not solving the whole problem yet. We're just solving a little bit of it. So we'll go out here. All right, so there is our 1 0 1 1 1 0 1 1. That's us walking it backwards. Okay? Now, what did my rules say here? I want to ask a question. If we're currently looking at a 1, we want to do something. Now, for right now, let's just make sure that we can accurately look at a 1. So I'm going to put a little sample question in here. I'm going to say if binary at position cur pos in string is equivalent to a 1, I'll print looking at a 1. Else, I'll print looking at a 0. All right, we're not going to need the else in this case, but we're just proving that we can accurately answer that question. All right, so we should see a looking at a 1, looking at a 0, looking at a 1, looking at a 1, looking at a 1, looking at a 0, looking at a 1, looking at a 1. Looking at a 1, 0, 1, 1, 1, 0, 1, 1. So we're accurately asking that question now. All right, now I only want to do something if I'm looking at a 1. Now, if we go back to our picture here, since I'm doing multiplication, I need to have these values here. I need to have the 1, then the 2, then the 4, then the 8, then the 16. I need to have that guy. I'm going to need access to that value. Okay? So before I do anything else, I'm going to back up. I'm going to say, okay, let's make sure that through my loop, I can produce those exact values. So I'm going to need a variable. I'm going to need to remember my current place. Okay, we'll go all the way back to what we said. We remember things, we ask questions, repetition. So I'm going to name that variable place, and I'm going to start it off at a 1. Why? Because the place always starts off as a 1. It's the base to the 0th power is always a 1. Okay? So I'll go ahead and print place. And then how do I get place to go from a 1 to a 2? I multiply it by 2. How do I get it to go from a 2 to a 4? I multiply it by 2. How do I get it to go from a 4 to an 8? I multiply it by 2. So I'll say place is equal to place times 2. Make sense? Go ahead and run this. 1, 2, 4, 8, 16, 32, 64, 128. Those are the values that we want out of there? Okay. So I got these guys taken care of. I got walking this guy taken care of. I got asking the question if I'm looking at a 1 taken care of. Now I need to decide, what do I do if I'm looking at a 1? If we're looking at a 1, we add the current place. So either the 1, the 2, the 4, the 8, the 16. We don't actually have to do the math because 1 times anything is that anything. Right? Okay? We'll add that to our running total. So now we're going to have a running total. So we're going to have to remember something else. And when we want to remember something, what tool do we use? Variables. Variables are how we remember stuff. How do we ask questions? If statements. How do we do loops? For loops, while loops. That's how we do repetition, right? You want to be familiar with what's in your toolbox. Okay, so if you want to remember something, we're going to need a variable. If we want to ask a question, we're going to use a conditional like an if statement. If we want to do some repetition, we're going to use a for loop or a while loop, something like that. Okay, so I'm going to need to go and remember something. I'm already remembering my place. Now I'm going to remember my sum. And we're going to start that off as 0. Because at this point, I haven't accumulated it to anything. Right? So now I want to ask my question. If binary at position, cur, pos, and string, if that guy is equal to a 1, if I'm currently looking at a 1, I'm going to say sum is equal to sum plus place. If I'm looking at a 1, I'll go ahead and add to my running total the current value of place. So what did we do here? I was looking at a 1. I'm going to add a 1. Was I looking at a 1 here? Nope. I'm not going to do anything. Am I looking at a 1 here? Yep. Add place. Am I looking at a 1 here? Yep. Add place. Yep. Add place. Nope. Yep. Add place. Yep. Add place. So if I'm looking at a 1, I'm going to set my variable name sum equal to whatever it's currently equal to plus the current value of place, which is equivalent to 1 times place. Now, does this line happen every single time, or does it only happen when this if is true? This line right here. When does this line happen? Every time through the loop? How do you know? It's not indented under the if. It's indented under the for, right? So this guy that I have highlighted is not part of this question. It's part of this loop. So it will happen every single time regardless of whether this comes out to true or not. Make sense? Okay. Now, when all is said and done, that is, when finished walking through my string, print the running total, which I happen to have remembered inside of sum. And there's my 221. That makes sense? And if I go ahead and bang out a bunch of other zeros and ones in there, and I run this guy again, I don't know what value that is, but that's obviously correct. So all right. So does it make sense how I went through this code? What's more important, I expect most of you to be able to look at this now and say, oh, that makes sense. But most of you had problems writing this yourself. And I'm going to guess that most of the folks that have problems writing this themselves did not go through this step where you drew the picture. You came up with a solution completely by hand, not thinking about Python, not thinking about any of these other things. You just solved it as a human. You said, look, I recently learned how to convert binary numbers into decimal numbers. That's a pattern I'm familiar with. I could solve as a person because we're great problem solvers, but you know, this isn't just second nature to me. I just can't visualize it in my head instantaneously. So I'm going to draw a picture. So we gave ourselves a sample binary number here. And then we reminded ourselves that strings are indexed from 0 to length minus 1, right? Then I reminded myself, okay, I need to keep track of what place I'm in. So this is the 1's place, 2's, 4. So I actually went and drew the picture. I said, this is what place we're dealing with in our example situation here. That way I can identify that pattern. I can say, oh, well, this number is twice of this number. This number is double this number. This number is double this number, so on and so forth. How do I accomplish that? Well, I just keep multiplying by 2 over and over and over again. And if I'm doing something over and over and over again, that sounds like repetition. So I'm probably going to pull that loop out of the toolbox and say, I'm going to use this for something. Okay, just kind of get our pieces laying in front of us. You know, you're preparing for the solution to this problem, but we actually haven't started coding yet. Now, I know that all of you want to sit down and just immediately start coding, right? Because that's what sounds like it's fun. But as many of you probably found out in this assignment, it depends what you're into, I guess, in terms of what's fun. But that was probably frustrating, a different F this time around, right? Eventually, you'll be able to solve problems like this without drawing the picture, but that doesn't mean that you didn't actually draw the picture. You just didn't have to put it down on, you know, a slide or on paper or something like that. You were able to just kind of visualize the solution inside of your head. You're still always doing that step of understanding the problem, solving the problem, then converting that solution into code. You have to have the algorithm. This is the algorithm for solving this problem. That makes sense? Here's the steps I need. I needed to remember some things along the way. So this screen here, this slide, gives me the picture that I need to think about all the things I needed to remember and how those things change throughout the thing and what I do at each step along the way. Only when I have that algorithm discovered can I then go and convert that into code. That makes sense? And once you see the code, I expect most of you can look at this and say, ah, that makes sense. Or that's easier than I thought it was going to be, or something like that. Now, many of you probably did not take this exact approach. I'm going to show you an alternative approach to this, because a few minutes ago, well, actually, let me first show you a weakness to this approach before we look at an alternative to the approach. This is an accurate approach, nothing wrong with this. Okay? But what if I wanted to convert this binary number? Well, actually, let's do an octal number. What if I wonder, does this guy let me refactor? Nope. We'll see how powerful the thing would be. Okay, so I'm going to say octal is equal to 129. Is that a legal octal number? What are the legal octets in a base 8 number? What are the legal digits in a base 10 number? 0 to 9. What are the legal bits in a binary number? 0 to 1. So 0 to the base minus 1. What are the legal octets in a binary or an octal number? Am I only using the language of 0 to 7 here, or do I have a little bit of a slip up? So this is not a legal octal number because I'm using a 9. That's not a legal octet. Okay, so I'll change that to a 7 in this example, but does that make sense? Okay, if somebody says here's a number and it's in base 8, you shouldn't find any values smaller than 0 or values larger than 7. If you do, they lied to you. Okay? Or they didn't know what they were talking about, one of them. All right, so this is an octal number. Now, I want to write the code that converts this octal number to base 10. What would change down here? If this guy was octal, this would go from a 1 to an 8 to a 64 to a 256. Is that 256 or 512? 512. So they jump, this is this number, times 8, times 8, times 8, times 8, instead of times 2, times 2, times 2. So if we look at our code here, we would change this guy to be an 8, correct? Now, is this question still valid? Will there be 1s in base 8s? Sure. But I'm missing some questions. We'll also have 2s in base 8s, and 3s, and 4s, 5s, and 6s, and 7s. Now, when I have a 1, we're still valid here, right? But if this guy's equal to a 2, I need to say sum is equal to sum plus 2 times place. If this guy is equal to a 3, three times place. If this guy is equal to a 4, 4 times place. If this guy is equal to a 5, 5 times place. 6, 6 times place. And a 7, 7 times place. Do I need to keep going? Those are all the octets, right? Go ahead.
Since you're doing pretty much the same thing over and over again, could you put all that in a loop with a variable?
We're in a loop.
Like,
You mean another loop? You could, but we're going to see this isn't a good way of doing it anyways. But you're right. That would be a suspicion. You would look at this and say, you know what? I'm asking about a 1, then a 2, then a 3, then a 4. If we had access to lists at this point, that could be beneficial to us. We could do it with a string. Walk through a string inside of here if it's equal to that, but we would then need to convert it to a. Actually, we wouldn't. I can show you. I'll show you that solution in a second. It's kind of interesting. All right, so we're saying if it's a 1, just add the place, because 1 times place is the place. If it's a 2, 2 times place. If it's a 3, 3 times place, so on and so forth. So will this convert whatever's in octal to decimal? Yep, so 127's in octal. I'm going to go through octal in reverse each time through. I'll ask, oh, it would have been nice if before I copied and pasted, I would have not used binary, but we'll just fix that real quick. So we're looking at our octal number now, right? Okay, and we'll add to our place. So if I go and run this, this will give me the octal version, or the decimal version of that octal number. So that's an 87. Okay, if I wanted to go to base 16, if it's a 9, or if it's an 8, if it's a 9, if it's a if it's a B, if it's a C, if it's a D, if it's an E, if it's an F. Get where I'm going with this? Lots and lots and lots of if statements. Okay, so now something that he said, so we'll just make this a little scarier. I'll go ahead and I'm going to create a, let's create a multiplier string. This is going to be a 0, 1, 2, 3, 4, 5, 6, 7. That's good enough for octal. Okay, in fact, I'm going to call this guy Octal Multiplier. All right, this 0, so we're going to assume in this case we don't know about that integer tool that int tool that can convert a char to a number. What position in this string is that 0? What bucket? It's in bucket 0, bucket 1, bucket 2, bucket 3, bucket 4. So we can actually use the position of it to determine, to get the multiplier. So you said, could we do a loop? So each time through, we want to ask a question. So we're going to have another loop. So we're going to say, cur pos in octal multiplier in range length of octal multiplier. Actually, we don't. We're going to start at 0. In range 0 to length of octal multiplier. And this is a normal step by 1. So we're going to go bucket 0, bucket 1, bucket 2. We'll ask the question, if octal in cur pos in string is equal to octal multiplier at bucket cur pos in octal multiplier, if that's true, if I'm looking at a char inside of octal that matches the current char we're looking inside of octal multiplier, I'll say sum is equal to sum plus cur pos and octal multiplier times place. So if it's equal to a 0, we'll multiply 0 times place. If it's equal to a 1, we'll multiply 1 times place. If it's equal to a 2, multiply 2 times place, so on and so forth. Octal equals... So there's our 87. Now, this is very likely significantly harder for you to follow right now, because this is a loop inside of a loop. Not crazy difficult, but we're talking about more advanced code at this point, and we got a lot of things we're trying to keep track of, but we saw it worked, right? Okay, so we could have made this more automated instead of having a zillion if statements. In fact, I'll give you a little hint here that might benefit you at some point in the future based on this. So this would be an 8, a 9, a 10, an 11, a 12, so on and so forth. This A is at bucket 10. This B is at bucket 11. This C is at bucket 12. That may or may not be helpful to you at some point in the future. Just hint, hint. Okay, so we'll call this an accurate solution, but probably not the best solution. So let's look at an alternative to this. So what I'm going to do here is I'm going to write some code that does not operate off of the asking questions premise. Instead, it just converts whatever character we're looking at into its number equivalent. Okay? So rid of this octal multiplier thingy, and we're going to say I want the int version of octal at bucket cur pos in string. So the current char I'm looking at, I want to convert that to an int, and I want to multiply that by place. And there's our 87. I didn't ask any questions. I just said, look, if I'm looking at a 1, if I'm looking at the char 1, turn that into the int 1. Char 2, turn it into the int 2, so on and so forth. That make sense? Okay. Now, I maybe am being a little wasteful here by saying if I'm looking at the char 0, turn it into the int 0 and then multiply by 0, which we know will always be a 0. But because we can write this code in a simplified way like this, we're saying, like, we're always going to do the math. If it's a 0, it's a 0. That's just the way things go. And we'll multiply a 0 by something else. We'll get a 0. We'll add a 0 onto our current sum, which will still be a 0 added onto our sum. Okay, math still works. All right, that make sense? All right, now, okay, so questions about this solution. This is probably your cleanest solution you could have had for the homework. You would have been operating off of ×2 and our binary number, but now one thing we could do is we could maybe change this to just say value and have a variable here maybe called base, and then operate off of a variable called value, and then multiply by base. So if value is 127 and we're saying it's in base 8, this will convert it to base 10. If I come in here and I just change value, well, actually, let's not even change value. Let's turn this guy into base 11. Is 127 a legal base 11 number? Yeah, what are the legal digits? What are the legal whatever it's for base 11? 0 to 9, then A. So it's 0 to 10, right? So the base minus 1. So it's 0 to 10, but we represent a 10 with an A. Does that make sense? So this code almost works for that right now. It'll work for this number. But if I threw that in there, we start getting a, it'll come in here and it'll say, I'm going to try to convert A into an int, and it'll scream. So you'll see that here right off the bat. I can't give you the numeric version of A. Don't know what that is. Okay? Questions about this? So as long as I don't put difficult to work with chars in there for us right now, this will work just fine. So there is the base 10 version of the base 11 number 127. Make sense? And all I have to do is I can change my value in here to whatever I want. I want to put some binary stuff in there, and then I advertise this guy as being base 2. I can now run this, and there's the decimal version of that base 2 number by just changing those inputs. Now, wouldn't it be nice? I mean, we've kind of done this in terms of all these individual little tools, right? Wouldn't it be nice if we ran into Home Depot and they actually had a machine, hopefully it's not too expensive, but called, base to decimal converter? Grab it off the shelf, and all you did is you drop 2 little things in here. Here's my number. Here's a string representation of my number. Here's the base that guy's in. Spit me out the decimal version of that thing. That'd be helpful, right? We've kind of written that code here. We've hobbled this guy together. We've prototyped this. This is how all your little electronic gadgets start off. They're in the lab somewhere where they have wires going everywhere, and they say, okay, it works, it's alive, blah, blah, blah. And then finally say, okay, we need to make this look pretty and throw it inside of some kind of container. All right? So they ultimately get to that. So we've proven how this can be solved. But it would be nice if we could write this code in a reusable way. All right? And that's where we introduce functions. This is a reusable chunk of code that we write once and can call multiple times. All right, now just like I said a few minutes ago, if we were at the lab, we're in the R&D department at some company, And we've said, okay, well, we think we have our generic solution here, right? We no longer need this binary thing. We have our generic solution. You set value to whatever you want your value to be. Then you say base is what base that guy's in. And the rest of this code then generically works, right? So what do we want to do? We want to stick this inside of a box with 2 little holes in the top of it, you know, for like your quarters. But we drop a number in and we drop a base in. And off the bottom, instead of a gumball shoots out a decimal number. So we're going to turn this guy into those things. So I'm going to take the guts. This is the stuff we want to hide. And I'm going to put it inside of a function. We're going to call it base to decimal converter. This guy's going to take in a value, and he's going to take in a base, and that's his logic. So now I could say print base to decimal converter. I can give it this value, and I can say that guy's in base 2. I can then call that same chunk of code again, giving him the number and say this is in base 8. So I have my magical box here that I bought from Home Depot called base to decimal converter. I toss it my value as a string, and I toss it the base it's in. The value comes in as a variable called value. The base comes in as a variable called base. This solution here is done in terms of those things. Now, right now, my base to decimal converter actually prints that answer out. What I wanted to do is I wanted to give me my answer. We expect the gumball to fall out of the bottom of the machine. So instead of printing here, we're going to return the sum. Return sends a value as output from a function. I'm going to put a big note here. A function that returns a value is different than a function that prints a value. It's okay for them to be different, but let me show you what I mean. Right now, this guy returns a value, right? And he's going to go through and we're going to call base to decimal converter. This is going to boil down to the value that is returned, and we're going to print that out. Okay, we get our 2 numbers. Now, if I left this guy up here as print sum, now this function does not actually return a value. It'll still print my answers because the function itself prints it. But then I'm saying I want to print the value that is returned by my functions. These functions do not return values. So I'm going to get none printed as well as my actual answers. This is me printing the returned value from that function, which was nothing. Make sense? It just so happened that my function did me a solid and printed out the value. There is a difference between functions printing a value and returning a value. If you want it to print a value, that's fine, but you're not going to be able to use that value later on. Okay? So we want this guy to go ahead and give us our result, and then we will receive it here and we will print it. Now, I can always put that in a variable. I can say answer is equal to whatever spits out of that function. And then I'm remembering that answer. I can print it if I want. But now I have access to that answer for later on. I can do multiple things with it. That make sense? All right, so for your homework, we are going to make base to decimal converter work for bases up to base, is it 37? Base 10 is 0 to 9. Yeah, up to base 37. That means work for bases that include legal its A through Z. Make sense? I remember earlier in class I said something about a hint hint. You might review that. All right, questions about homework for Wednesday? I'll put this code up on Slack for right now. So what you have here is a starting point that will work for any base between 0 and 10. Anything bigger than that, you're at the mercy of whether or not they use A through Z's in the number, which are legal for numbers bigger than that, right? So, with me? All right, I will see everybody on Wednesday. I'll look at the book. I might give you a reading assignment as well, but I want to see how far the next chapter goes. So I might just stick with this. I'll look here in the next hour or so.
Please don't assign the whole book.
Well, I won't. It won't be the whole thing. Well, it's good for your constitution.